Hello. So this is my final presentation about something called the Curry-Howard correspondence and its many implications. My main reference for this paper is from Philip Wadler's Proposition as Types. This paper is a short exposition on the discovery and rediscovery of models that try to define something called effectively calculable functions with the goal of solving the decision problem. As recap, the decision problem is this yes or no problem saying, is there a general procedure given a mathematical statement, whether or not you can find that to be true or false? As we know, this is not solved. So the paper covers three things: Church's lambda calculus, Kurt-Gödel's recursive functions, and Turing machines, all of which were determined to be equivalent. In relation to lambda calculus, it then moves on to mention how Haskell Curry and Howard at different times, late 1940s and late 1960s, became curious that the function types A to B can be read as logical implication. A implies B, and vice versa. Following this intuition, Howard made the observation with the deepest implication, and that proof normalization corresponds to program evaluation. We will get back to this later. So this is just a simple outline. We have to discuss what Curry-Howard correspondence is, its implications in computation research, and its relevance to my thesis interests. The Curry-Howard correspondence, also known as Curry-Howard isomorphism, proposition as types, or proofs as programs, it's a correspondence between logic and programming, to put it simply. This is it at the surface level. So we have two fields here, or two realms, the realm of logic and the realm of programming. If you have a formula A in logic, you can interpret that as a type A in programming. If you have a proof in logic, which is a tree of inference rules, that just means in programming you have a term. If a formula is true, that means type A has an element. If a formula is false in logic, in programming, you could say that type A has no elements. Truth in logic can be interpreted as the unit type in programming, which is a special type that contains only this as the sole value. As for false in logic, we have in programming the empty type, or you could think of this as none or void. So this is the type that has no elements. Implication. A implies B. In programming, that would be a function type from A to B. In logic, conjunction, A and B, it corresponds to product types, A times B. In logic, we have disjunction, A or B. Its equivalent in programming would be some type A plus B. And universal quantification results to something called dependent product types in programming. So I won't discuss this in detail, but dependent types are types whose definitions are based on values. So in comparison with the normal type, let's say the type string or the type number, whose members are the integers, for example, that's a typical type. But then dependent types are types whose definitions are based on values. So these are essentially functions that produce types themselves. So for example, if you're worried about array index out of bounds, which is a common problem, right? In programming, you access an array in which the index corresponds to a cell that does not exist. That's going to be a dynamic failure at runtime. So one usage of dependent types is you can encode unique array types in which the size is also known at the compile time. So that's one benefit of it. And lastly, existential quantification can be corresponding with dependent sum types in programming. This is what's happening at the surface level. At the proof theory level, we have the following examples, but this is just one of the many. So for example, you are given a proof. So the ellipsis here mentions that you can think of this as uh, a proof tree, and then some of these are just omitted. So if you want to introduce an implication, you can simply pick any formula and then pick another formula somewhere lower than somewhere down the line, and then you can say that A implies B. So this is an introduction for implication. Uh, it has a correspondence with function abstraction in lambda calculus. So for example, if you have a tree of computation, let's say you have a variable with type X somewhere, and then somewhere down the line, you have a lambda term whose type is B. You can then create the function lambda X, and then inside the body is the lambda term M. And the type of this whole expression is A from B, because the input of X has a type A, and then this produces a type B. So the name of the rule would be abstraction. So that's for introducing things into proofs, or so it's like defining variables in a program. So how would you consume it? So this is its dual. In logic, there's modus ponens. We are familiar with this. You are given an implication A implies B, and if you also happen to have A, that means you can conclude B, modus ponens. This has a correspondence with function application in lambda calculus. So if you have a lambda term M whose type goes from A to B, which implies that it's a function, and you have another lambda term N somewhere whose type is A, if you apply M to N, so that's function application, N would be the argument to M, the type of this would be B. So that's function application in lambda calculus, having a correspondence with modus ponens in logic. So what are the implications of this? So implications of the Curry-Howard correspondence is just abbreviated to CHC. So as you notice, I'm going to be precisely giving the citation here because these are not my exact words. With the introduction of dependent types, these are the analogs of quantifiers, universal and existential quantifiers. Proofs in predicate logic can be represented by a term in some suitable type lambda calculus. So remember that the proofs in predicate logic can be represented by a term of some type in programming. The developments of this led to something called the calculus of constructions, which is essentially the backbone of the proof assistant. Second order logic, we've gone through this over class. It's a propositional logic that includes quantification, existential, and universal. So second order logic corresponds to something called polymorphic lambda calculus, or sometimes called system F, which is a lambda calculus with type abstraction, which eventually got adopted as generics in Java and C#. So the benefit of type abstraction and eventually generics is that you have to write less code. So for example, if you have a standard library dealing with concatenation or addition of things, what does addition mean for numbers, for example? What does addition mean for strings? Instead of writing some addition function for all of those types that you have, you can just have something generic, and then the developer would just have to implement what it means for their program to have addition. Of course, in our programming language ecosystem nowadays, you can expect to have, let's say, if you have arrays, addition of arrays would just be concatenating the arrays from tail to head of the next array. You have addition of numbers, you have concatenation of strings, that sort of thing. So this is the backbone for that. this discovery of correspondence between second order logic and polymorphic lambda calculus. When the Curry-Howard correspondence is applied to classical logic, a type was discovered for the call CC operator in scheme, which is a versatile control flow operator. So CHE is originally applied to something called intuitionistic logic, which I believe I mentioned before. This is the logic in which the law of excluded middle is rejected. Remember that the law of excluded middle says that either A or not A, whatever A is, this whole thing is always true. But in intuitionistic logic, the intuitionistic logicians reject this idea. So for this to be true, you have to prove that A exists or that not A exists. So you can see the language being used here. The proof of A can be thought of again as the term of some lambda calculus. So they can be used interchangeably like that. So Curry-Howard correspondence originally came from the idea in intuitionistic logic that in order to prove things, you have to prove the existence that says that something really exists. So in that sense, you're looking for types that can be given terms. That means a type has an element. So that leads to things being true. Again, relating intuitionistic logic and classical logic via Curry-Howard correspondence resulted in the discovery of something called continuation passing style, which is a style of programming where control flow is explicitly passed to continuations, with continuations meaning the rest of the program. Yeah, compare this to when you're writing in a procedural language like C. Uh, unless you're using if statements, you just go from one line to another, right? But in CPS or continuation passing style, this is not the case. For every computation that you do, you have to explicitly pass in what you need to do next, which is essentially just the next fragment of the program. Actually, continuation passing style is not something you would do as a programmer, as a human. It's more in tune with writing compilers because the continuations are a great importance to programming language theorists exploring concurrency, for example, because you can fine tune what happens next in a program using continuations. So that's its relevance. In modal logic, with its interpretation of necessarily and possibly, with the possibly true interpretation having a computation correspondence that led to the creation of something called monads. So if you ever tried to program in Haskell, this is an infamous control flow feature that handles side effects such as input-output and exceptions and random number generation in an otherwise pure functional language. Finally, as mentioned in the paper, linear logic is a kind of logic in which hypothesis is used exactly once. And from this logic, if you give it a Curry-Howard correspondence treatment, there exists a corresponding linear type system in which the interpretation now would be that variables must be used exactly once. And then there are other types of type systems that are sort of the siblings of the linear type system, and they're called substructural type systems. So an example would be affine. So in an affine type system, you have to use variables at most once. If you don't use them, it's okay. Relevant type systems, you have to use things at least once. And finally, ordered, you have to use them in the order of introduction. And all of these type systems have their own equivalent logics with the same ideas. For example, in affine logics, you have to use hypothesis at least once, and so on. So how is this relevant to my thesis interests? So my recent 2025 WCTP paper on workflow models is inspired by Curry Howard correspondence, actually. So in that paper, I looked at workflow models and then I looked at something called places in them, and I was able to view them as variables. And then transitions inside workflow models, I viewed them as functions, and each of these have their own types. The requirement for the presence of n tokens corresponds to the usage of product types. So this is mostly used for n joins. So if you have an n join, that means it has to have all the tokens available for it to fire. So the way you represent that is using product types, because again, product types can only exist if all of these things have terms with them, which also corresponds with uh, conjunction, in which the entire formula only becomes true if you have a proof of A and a proof of B and C and so on. The requirement for the presence of exactly one token, in the case for OR joins, corresponds to the usage of some types on the other hand. And finally, the future work of ensuring that all tokens get used up after the workflow completes its run can be done by making this type system linear. So the ideas in that paper, the approaches I took are taken from ideas of Curry-Howard correspondence. It's not just one logical approach to doing things. It's not just one logical technique, so to say, but it's a bunch of ideas with duals with them, in which uh, you can extend whenever you are doing research, especially with programming languages. And this is my reference. And this paper is short, but it also references many other seminal works on the development of Curry-Howard correspondence, which I will be expounding upon on the paper. Thank you for listening.